Great. So welcome back after lunch. And I will be talking about the FRI protocol and in particular testing proximity to low degree polynomials. And in this talk, I'll be talking about the original FRI protocol, a particular component which is crucial to analyzing the soundness of the FRI protocol, which is proximity gaps for Reed-Solomon codes. So I'll tell you about that, and then we'll see connections to the soundness of FRI, and then we'll end with a very interesting open question related to it. Okay, so here's the setting, which is again very similar to what Swastik talked, then maybe Ale's setting. So we have an underlying finite field FQ, and there is an evaluation domain of size n sitting inside this field. And we're going to test proximity to low degree polynomials. So D is going to be the degree of the underlying polynomial. Think of D to be 0.1, and it doesn't have to be that, but that's just some parameter to keep in mind. And so the setup is like we've seen in the last few talks. So you're given a function f, which is evaluations of this function on the domain S, and we are given it as a table of entries which we have query access to. So you can query the value of f at any point of the domain. And some of the questions you could ask are, does f look like a low degree polynomial? The evaluations of a low degree polynomial. Is f close to the evaluations of a low degree polynomial? So other than on a few locations, does it look like a low degree polynomial? And it's not hard to see that you cannot answer this question without making lots of queries into f. So D, the degree is linear in n. You need to make at least linear number of queries to determine this, unless there is some additional help. And so this motivates the model of IOPs and IOPPs, which we saw in the previous talks. But before I get into that, just to set up some notation that I'll be using. So you have the finite field, you have your evaluation domain. I'll talk about the Reed-Solomon code over this finite field on the evaluation domain S and for degree D polynomials as a set of those functions which are true evaluations of degree D polynomials. And so every such evaluation of a truly low degree polynomial can be viewed as a vector in FQ to the n. And so the set of all low degree polynomials, if you identify them as a particular set of vectors in FQ to the n, this forms an error correcting code. Just because two distinct degree D polynomials can't agree, they can agree in at most D locations. Any two distinct polynomials, their sets of evaluations are far apart. So it gives you an underlying code. That's the Reed-Solomon code. We'll be talking about this code a lot. We just heard a talk from Madhu about it as well. And now the question of, given query access into F, determine if it's close to a low degree polynomial or not is equivalent to verifying if this function F is close to a code word of the Reed-Solomon code. Okay, so that's the problem we are most interested in. And we don't want to make linear number of queries into F to determine this. And so we are going to be in the IOPP setting, where there is a prover who's interacting with a verifier, and the prover can write down proofs, so long strings which the verifier will probe in few locations to determine if f is a low degree polynomial or close to a low degree polynomial or not. And if f has the property, if f is truly low degree, we would like the verifier to be convinced and to accept with probability 1. And if the string is far from being low degree, we would like the verifier to reject with high probability, as high as possible. This is the soundness of the protocol. And this is one quantity we're going to be particularly interested in this talk. Good. So the FRI, as now you've seen in almost all the previous talks, it's a beautiful protocol which gives a really fast, efficient algorithm for this problem with exciting, interesting, concrete parameters. And it's a central ingredient which shows up in several zero-knowledge proof systems as well as stacks. I won't talk about the full FRI protocol, but I will talk about a particular component of the FRI protocol, and which is crucial in analyzing the soundness of FRI. Okay, so the main building block of FRI, and again we saw this in Swastik's talk as well as Ali's talk, is a sketch or a folding. So you have a function evaluated on a domain of size n, this algebraic sketch of folding gives you a way of taking a function and compressing it to another function, f prime, on a domain of size n over 2, if you do a 2-to-1 folding. And it takes a random series input and computes this map. I will briefly describe what this function is, but we don't really need to go into the details of what it is for the purposes of the talk. But this algebraic sketch has 3 nice properties which make it useful for FRI. One is that f and f prime, the consistency between these 2 functions can be checked locally, because each entry of f prime depends only on 2 entries of f. So this is important. This mapping is low degree preserving. So f is truly a low degree polynomial, then f prime will also be low degree. And perhaps the most non-trivial and interesting property is the farness preserving property, which is if f is far from being low degree, then so is f prime and vice versa. So this is the property we're going to focus on for much of the talk. So just a quick recap, where did f and f prime come from? So suppose you start with a truly low degree polynomial f, and it looks like that. It's a degree d polynomial. You can break f into its odd and even coefficients and write f of t as g of t squared plus t times h of t squared. So you can, this is using the FFT transformation, you can get access to g and h. And if f is truly low degree, then it's not hard to see that g and h are also truly low degree. So f is degree d, g and h will be degree d over 2. Good. So what we're going to do is take g and h and take a random linear combination of g and h and call that the polynomial f prime, which is now another degree d over 2 polynomial, a single degree d over 2 polynomial that you derive from f. And what goes on in FRI is we want to check proximity to low degreeness of f. In one round, you can reduce it to checking low degreeness of f prime. And this transformation from f to f prime, there's locality. You can check consistency locally. It's easy to see that f is low degree if and only if g and h are low degree. But what is non-trivial is the farness preserving property. Is it true that f is far from low degree if and only if g and h are far from low degree? This is a little bit less clear, and this again I'm going to be talking about. But this is a crucial component in the analysis of the soundness of FRI, and it shows up in a variety of different scenarios, not just in FRI. This phenomenon arises. Okay, so let's focus on the farness preserving property. Let's forget how G and H came about, and we'll focus on this act of taking random linear combinations of 2 functions. So we're given f on a domain of size s. In this transformation, what we got was there was a subset of the domain s prime and 2 functions g and h defined on s prime. And we saw that f is a true Reed-Solomon code word for the Reed-Solomon codes of degree d, if and only if g and h are Reed-Solomon code words for the domain s prime and degree d over 2. It turns out that if you think about it for a few minutes, this is a robust statement in that if f is close to these 2 Reed-Solomon codes, then g and h are also going to be close in Hamming distance to the appropriate Reed-Solomon codes. Good. So that was one step. From f, we got these 2 functions g and h, but then we took g and h and we took a random linear combination of g and h to get one single function, which we called f prime. And what we really wanted to argue was that f prime had this farness preserving property with respect to f. If f was far, f is far if and only if f prime is far. So if we know that g and h are true Reed-Solomon codes, if g and h are true Reed-Solomon codes and we take a random linear combination of g and h, it's not hard to see that g plus z times h is also a true Reed-Solomon code. because adding code words and multiplying by scalars doesn't change the property of lying in the code. But what we really care about is, does this equivalence also hold in the robust sense? So is it true that if G and H are close to Reed-Solomon codes, then G plus CH, ZH is close to Reed-Solomon code and vice versa? For instance, does the farness preserving property hold for G and H with F prime? So is it true that G and H are close to Reed-Solomon codes if and only if G plus ZH is close to a Reed-Solomon code? And this is the question we want to focus on. It's a bit high pro. So I'll take for a random Z, suppose G plus ZH is close to a Reed-Solomon code, of this Reed-Solomon code. For many Zs, and I'll quantify explicitly what I mean. So suppose for a random Z with high probability it holds over the choice of Z, that G plus ZH is close to a Reed-Solomon code. Can you deduce from that G and H themselves are close to Reed-Solomon codes? And this is a priori not clear that it needs to be the case.
Just to check the top thing, it's not completely obvious, but relatively easy to prove.
Yes. Yes.
But it's not totally obvious.
Up to a factor of 2, I think it is obvious. But suitably defined, let's not worry about that. So about that factor of 2. But so this first, yes, another question. Closeness is in Hamming distance. So I say a function f is close to a Reed-Solomon code. Is epsilon close? If when I change epsilon fraction of the coordinates, I get a true code word. So I'm defining closeness with respect to the Hamming distance. Any other questions? Okay, so this is the relationship between. So let's forget how we got G and H. The question we're going to study is, G and H are close to Reed-Solomon codes. No, sorry, G and H are 2 strings, and I look at the linear combination of G and H, and I'm asking, is it true that G and H are close to Reed-Solomon codes if and only if G plus ZH is close to a Reed-Solomon code for many choices of Z? That's what I want to understand, and this turns out to be a crucial ingredient in analyzing the soundness of FRI. Okay, so this is the question of this. This is the proximity gaps question for Reed-Solomon codes, and I will and it's the result I will talk about is from this latest paper BCIKS, but it builds upon a sequence of works analyzing the proximity gaps. Only if, I think one direction is easy. One direction is easy. If G and H are close, F prime is close, but if G and H are far, I want to show that F prime is far. Exactly. One direction is easy to see. G and H are close, then F prime is close. If G and H are far, can it be that F prime is close, or is F prime, does F prime need to be also far? Exactly. Thank you. So one direction is straightforward. Okay, so let me tell you what our final theorem statement is, but let me first, let's do it in pictures. So we have the underlying Reed-Solomon code. So we have our space is FQ to the N, and our code words are vectors in this space. And they're all far apart from each other. Let's draw a ball of Hamming radius delta about every code word. So think of delta to be some fixed constant. And when I say Hamming ball of radius delta, I mean, let's look at all those vectors which are in Hamming distance at most delta times n from a code word. Okay, so I consider these balls around every code word. Then the proximity gap statement, which I will make explicit, mathematically explicit very soon, is saying this. Now let's take, I'm in FQ to the N. Let's take any line in FQ to the N. Then one of two things must happen. Either that line passes through very few of these delta radius balls, or, sorry, not that it passes through very few, good. Each point in FQ to the N Each line has n points on it. So out of the n points on the line, sorry, q points. Each line has q points on it. Either very few of these points lie within these delta radius balls. If many points on the line fall within the delta radius balls, then all points on the line must fall within delta radius balls. There's no in between. You can't have a line where half the points lie within delta radius balls. Either all points of the line hit these balls of radius delta, or just a teeny tiny fraction of the points on the line fall within balls of radius delta. This is what the proximity gap statement is. And now let me make explicit what is delta, how tiny is teeny tiny, etc. Any questions? Okay, so let's me make a mathematically precise, somewhat precise statement. I don't think I'm going to be super precise. So G and H are two arbitrary functions from a domain of size n going to FQ. So you can view them as vectors in this vector space FQ to the n. Now let's look at the line G plus Z times H. So G and H are vectors, Z is a scalar. So as Z varies, G plus ZH is the whole line. Suppose that for many points on the line, so for an epsilon fraction of the Z's in FQ, which means suppose for many points on the line, the points lie within these balls of radius delta. So that's exactly what I'm saying here. The distance of G plus ZH to a Reed-Solomon code word is at most delta. Then it must hold that all points on the line lie within balls of radius delta. So for all Z in FQ, which means all points on the line, that point is close to a Reed-Solomon code word. And in particular, even G and H themselves must be lying within balls of radius delta. Okay. What is delta? So what is epsilon? So the best epsilon we are able to prove it looks of the form n squared over q. So for instance, if the field size is much larger than n squared, then this n squared over q can be made tiny. So think of q being n cubed or at least n cubed. Then even for a tiny fraction of the points, if you lie within balls of radius delta, then for all points, you lie in balls of radius delta. And what is the delta that we can take? So we can show this for all values of delta, where delta goes all the way up to the Johnson radius for Reed-Solomon codes. So for all delta all the way up to 1 minus square root the rate rho, or 1 minus square root d over n, such a statement holds. Good, so that's the proximity gap statement. Is it tight? It really depends on the list decoding radius of Reed-Solomon codes themselves. It is possible that we can do this for delta going all the way up to 1 minus the rate. We don't know that it needs to stop here. But in order to make it go beyond here, we would have to prove better bounds on the list decoding radius for Reed-Solomon codes.
Moreover, it's very interesting, but do you need it actually for the analysis for FRI?
No. So what we show is that for G and H, there's some correlated agreement. In G and H, when we say agree with Reed-Solomon code words, what we will prove is that they agree with Reed-Solomon code words, and in fact on the same set of coordinates. The agreement is going to be on the same set of coordinates. It's correlated agreement, and then the moreover just follows from that. So what we do need is this correlated agreement, not that G and H are close to code words, but they agree with code words and the agreement is on the same set of coordinates. So we do need that, yes. Correlated agreement, and then the moreover just follows from that. Okay, so I don't have too much time, but let me say a couple of words about the proof and a couple of words about applications. So we know that for many Z's, G plus ZH is close to a Reed-Solomon code word. We want to deduce something about G and H themselves. What we will use in our proof is, so the statement I'm looking for is completely combinatorial. It's not algorithmic at all, but still underlying in the proof, what we will use is, in the analysis of the combinatorics, is the decoding algorithms for Reed-Solomon codes. In fact, the same algorithms that Madhu talked about, the Berlekamp-Welch algorithm and the Guruswamy-Sudhan algorithm, are going to be crucial in the proof. And okay, so that's what I said. Let me keep going. So let's just look at this picture. So I'm just trying to interpret what we have. So this squiggly blue line on the left. So G is a vector of length n. Let's plot this vector of length n and get a curve for what G is. It need not be, we don't know that G is close to a low degree polynomial. It's some weird curve. And FH is some weird curve. But what we're doing is we're looking at G plus ZH. So we're connecting these two curves by straight lines for the n different straight lines connecting these two curves. And now we're looking at cross sections of, so we get this weird surface, and we're looking at cross sections of this surface for different values of Z. And we know that for many values of Z, this object, this weird curve that we get is close to a low degree polynomial. And we want to deduce that the entire surface that I have drawn here is somehow close to a low degree surface. And good. So for many cross sections, the green curves are close to low degree polynomials. Can we get a single low degree surface explaining this object? And so the main idea that we use is, again, decoding algorithms for Reed-Solomon codes. We know that for many choices of little z, f of x plus z times g of x is close to a Reed-Solomon code, and hence if we run the Guruswamy-Sudhan decoding algorithm on it, the algorithm will succeed in finding a nearby code word. Good. We want to run this. We know this is true for many z's. The way we take into account the information of all z's at once is to consider little z replaced by a formal variable capital Z, and look at the function f of x plus z of z times g of x, where we don't substitute z to be the little values, the field constants yet. We view it as a global variable and run the decoding algorithm for this much stranger object, f of x plus the formal variable times z times g of x, and just start running the decoding algorithm and see where we run, what obstacles we run into. And what we eventually show is that the decoding algorithm does succeed when we run it on this larger space. And the way we show that the decoding algorithm succeeds is by using that for many evaluations of capital Z to little z, it succeeds. And then we want to stitch all that information together to show that even for the global variable capital Z, it succeeds. And once it succeeds, when z is of this formal variable capital Z, everything else follows. That means for every choice of capital Z to little z, it will succeed, and we get what we want to get. And the Guruswamy-Sudhan algorithm works up to a certain radius. Our proximity gap statement works up to that exact same radius as the decoding algorithms work up to, which is the Johnson radius for Reed-Solomon codes. So I'm basically out of time, but this analysis immediately improves the soundness of FRI to this quantity. If your polynomial is delta, if your input function is delta far from polynomials, then you'll reject with probability at least delta, as long as delta is less than 1 minus square root rho. But whether this 1 minus square root rho needs to be there, we do not know. The list decoding radius of Reed-Solomon codes, understanding that is important in improving the soundness further. Batched proximity testing. Here's another very interesting setting. I'm out of time, so I'm going to stop. But if you want to check that a bunch of polynomials together are all close to being low degree. If you take a random linear combination of them and you get a new function, it suffices to check that that is low degree. If that is low degree, it will imply that each one of the previous functions is close to low degree. And this is a direct consequence of the proximity gap statement that I made. I'm going to skip, I'm out of time. So I'm going to not talk about deep FRI, but deep FRI is a related protocol which close to what Ale talked about, but which has the potential of improved soundness if you can get better list decoding for Reed-Solomon codes. This is my last slide. What is the question of list decodability of Reed-Solomon codes? Is understanding what's the largest radius for which you can, if combinatorially prove that there are not too many code words in a ball of that radius. And understanding the largest radius to which we can decode is crucial in improving the analysis of FRI and deep FRI. So I will stop here, and thank you very much.
Questions?
Yes.
So my cryptography math is not great, but what is the significance of that proof with respect to the closeness?
The closeness is what, so we showed that if you start with an input function f that is quite far from being a low degree polynomial, then this new function f prime that we get, so we break it up into g and h, and the new function f prime we get would also be really far from low degree polynomials. This is one round in the FRI protocol. So if you can preserve farness, then you won't be able to, so eventually the verifier will be able to catch that your input is not close to a low degree polynomial, because in the protocol you'll eventually make queries. So you'll reduce from f to f prime to f double prime. You'll keep getting functions on smaller and smaller domains, and eventually it will be down to a constant size domain where you can just check if your function is close or far from a low degree polynomial. But it's crucial within this protocol that if your function was far from low degree, you preserve that it remains far from low degree, so that in the end you detect that with high probability that your original polynomial was not close to a low degree polynomial. So the probability of catching a cheating prover depends on how far you keep the function.
So you just put a threshold into the closeness, and if it's far away, then you just kind of know, okay, we can throw this out.
Yeah, if it's far away, you'll be able to catch it with high probability. Yep. Exactly. The further away it is, the higher probability with which you can detect. You'll be able to catch it. Yes?
Yeah, so I just wanted to mention in the unique decoding regime, you
Yes.
have a result with false witness probability n over q, right?
Yes.
Just to let you know, so it's that result, it cannot be sharpened. So
yes.
I was able to come up with counterexamples where you actually attain n exactly.
Yes.
There is a lower bound in your paper that attains e plus 1. As opposed to n. So I just wasn't sure if you're aware that.
Oh, n versus n plus 1, you mean?
E plus 1. So you have a counterexample that attains e plus 1, right? This is this
is the number of points on the line.
Exactly. Yeah. Yes. So this is the number of close points on the line before you get the guarantee of correlated agreement. It's easy to show that you can get e plus 1 points.
Okay.
In fact, you can even get n points. Of course, you can't get more. We know that you can't get more than n, but you can attain exactly n.
Okay.
So in other words, the right-hand side cannot be decreased in the unique decoding regime. I can share more.
Sounds great. Let's talk about it offline. I'll be very happy to hear about it. Thank you. Thank you.